Imagine a scene unfolding in November of 1918, where the brightest engineering minds across the European continent were confronted with a seemingly insurmountable challenge. The Great War had finally concluded, yet its brutal lessons were indelibly etched into the very fabric of every ravaged battlefield, from the blood-soaked fields of Verdun to the churned earth of the Somme. The stark reality was undeniable. Conventional wheeled vehicles alone were no longer adequate to secure military victory. Trucks frequently became mired in the unforgiving terrain, tanks suffered constant mechanical failures, and armies desperately needed a more effective means of transporting both personnel and heavy armaments across landscapes that eerily resembled the desolate surface of the moon. This pressing need marks the genesis of our narrative, situated within the peculiar confluence of two seemingly incompatible concepts that, against all odds, were destined to merge. The ingenious idea of the half-track did not materialize from a vacuum. Its origins trace back to 1915, when a gifted French engineer named Adolphe Cagrès was employed by Tsar Nicholas II in Russia. His mission was to ensure the operational continuity of the imperial family's automobiles amidst the formidable challenges of the Siberian snows. Cagrès' innovative solution involved replacing the vehicle's rear wheels with flexible rubber tracks, while retaining the front wheels for precise steering. This approach was remarkably simple, profoundly brilliant, and, crucially, proved to be highly effective. By 1919, the renowned automotive manufacturer Citroën had acquired his patents and commenced the production of vehicles incorporating the Cagrès-Hinton system. This development unequivocally demonstrated that this hybrid design possessed the capability to navigate terrain that completely incapacitated purely wheeled vehicles. However, at this juncture, the military applications of this technology were not yet a primary consideration. The focus remained solely on facilitating unimpeded travel from one location to another, even when confronted with nature's most formidable obstacles. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. As the 1920s progressed, military strategists began to pose increasingly uncomfortable questions regarding the efficacy of existing transportation methods. Tanks, while undeniably potent, were agonizingly slow. The formidable British Mark V, for instance, could barely achieve a speed of 4 miles per hour on a favorable day. Conversely, trucks offered impressive speed but became utterly useless the moment they ventured off paved roads. Infantry units continued to march on foot, much as they had during Napoleon's campaigns, a practice that inevitably meant armored divisions would surge ahead, only to be compelled to halt and await the arrival of the rifle-carrying soldiers. Remarkably, even the Germans, despite their recent defeat in the war, were already meticulously sketching out nascent ideas for improved mobility. The Soviets, too, were actively engaged in experimental endeavors. Even the Americans, who had made minimal use of tanks during World War I, initiated their own exploratory designs at the historic Rock Island Arsenal. The profound allure of the half-track lay in its audacious engineering compromise. It offered approximately 70% of a tank's exceptional off-road prowess, while simultaneously retaining about 80% of a truck's commendable speed and mechanical simplicity. The presence of front wheels afforded respectable steering capabilities without necessitating complex track braking systems. The rear tracks effectively distributed the vehicle's substantial weight across challenging surfaces such as mud, sand, or snow. Furthermore, precisely because power was not being transmitted to all four corners via tracks, the entire assembly was inherently lighter, more economical to produce, and considerably simpler to maintain than a full-fledged tank. In 1931, the United States Army conducted trials with the Cunningham T1, which was essentially a conventional truck retrofitted with tracks on its rear. While its appearance was undeniably unconventional, even bordering on comical, it possessed the remarkable ability to traverse trenches that would have completely immobilized standard trucks. By the mid-1930s, the grim realities of global politics began to crystallize. Germany was clandestinely rearming itself, circumventing the restrictions imposed by the Treaty of Versailles. Japan was aggressively expanding its territorial claims into China with rapidly mechanizing columns. The Spanish Civil War, which raged from 1936 to 1939, served as a crucial proving ground where all belligerents absorbed the same harsh lesson. Modern warfare demanded that infantry maintain pace with armored units, and, crucially, they needed to arrive at the battlefield prepared to engage, not utterly spent from a 20-mile march. The half-track was rapidly evolving beyond a mere clever contrivance. It was becoming an indispensable military asset. Engineers in industrial centers such as Detroit, Stuttgart, and Moscow were engaged in a frantic race to solve an identical, pressing conundrum: how to construct a vehicle that possessed the combat capabilities of a tank, the hauling capacity of a truck, and the firepower of artillery, all while maintaining a production cost low enough to facilitate the manufacture of tens of thousands of units. This pivotal question would ultimately shape the design of the formidable machines that would soon roll into Poland, traverse the battlefields of France, navigate the harsh deserts of North Africa, and eventually spread their mechanical might across half the globe. The era of the hybrid warrior was unequivocally dawning, poised to enter the crucible of war. The American approach to developing the half-track mirrored their characteristic industrial philosophy of the 1930s, an unwavering focus on mass production from the very outset. While European designers were meticulously crafting bespoke, highly specialized solutions, engineers at the White Motor Company in Cleveland and Autocar in Pennsylvania were envisioning vast assembly lines capable of churning out vehicles by the thousands. This pragmatic vision ultimately culminated in the M2 and M3 half-track family, machines that, despite their outwardly stark and utilitarian appearance, concealed genuinely ingenious engineering beneath their boxy steel panels. At the core of these vehicles lay the power plant. White Motor ultimately selected the Hercules JXT inline six-cylinder engine, a robust 386 cubic inch gasoline motor that generated 147 horsepower at 2,800 revolutions per minute. While this figure might seem modest by contemporary standards, its true significance lay elsewhere. It was exceptionally reliable. Furthermore, it could be manufactured with remarkable speed, and mechanics already familiar with civilian trucks possessed the requisite knowledge to service and repair it with ease. The engine was conventionally positioned at the front, in the manner of a standard truck, which facilitated straightforward heat management and allowed for convenient access without requiring the disassembly of the entire vehicle. These half-tracks achieved a maximum speed of 45 miles per hour on paved roads, a figure that typically decreased to approximately 25 miles per hour during cross-country travel, depending on the specific terrain. This speed was deemed sufficient to maintain pace with tank columns, yet not so excessive as to transform the journey into a jarring, bone-rattling ordeal for the 10 infantry soldiers seated in the rear compartment. The transmission system was where the White engineers truly distinguished themselves. They devised a sophisticated 4-speed manual gearbox complemented by a 2-speed transfer case, providing the driver with a comprehensive total of 8 forward gears, in addition to 2 reverse gears. This extensive range allowed the vehicle to painstakingly ascend a 60% grade in first low gear or to effortlessly cruise at highway speeds in fourth high. Power was channeled from the transmission to a front axle for the wheels and a separate drive shaft extending rearward to the track assembly. The front wheels retained their conventional pivoting capability for steering, but here lay a crucial innovation. The driver was also equipped with brake pedals that could independently slow individual tracks. This ingenious feature enabled the half-track to execute sharper turns than could be achieved by the front wheels alone. While mastering this system demanded considerable skill, experienced drivers were capable of practically pivoting these formidable machines in place. The track system itself epitomized American pragmatism. Rather than utilizing metal links, akin to traditional tank treads, the M2 and M3 employed innovative rubber block tracks developed by the Firestone Tire and Rubber Company. Each track was meticulously constructed from steel cable embedded within rubber, onto which 110 individual rubber blocks were vulcanized. These blocks, roughly 5 inches wide, were specifically shaped to provide superior grip on dirt, mud, or snow. The brilliance of this design was multifaceted. First, rubber tracks were inherently quieter than the clanking of metal on metal, a significant advantage for tactical stealth. Second, rubber exhibited greater durability on paved roads, preventing both damage to the highway surface and premature wear of the tracks themselves within a mere 100 miles. Third, in the event of damage to a track section, individual blocks could be replaced in the field, eliminating the need to swap out entire track assemblies. The suspension system was a modified vertical volute spring system. Essentially, large coil springs were mounted vertically behind each of the 4 road wheels on every track assembly. As the vehicle traversed obstacles, these springs compressed, effectively absorbing the impact. Was the ride smooth? Candidly, no. Traveling in the rear of an M3 over rugged terrain was often likened to being inside a cement mixer, yet the system was undeniably effective. It was simple to maintain, and, most critically, it distributed the vehicle's substantial 20,000-pound combat weight across a sufficient surface area to maintain ground pressure at approximately 10 psi. For illustrative comparison, a fully loaded truck might exert a ground pressure of 40 psi, a stark difference that explains why trucks frequently became mired in mud, while half-tracks continued their relentless advance. Production escalated at an astonishing rate once America formally entered the war in December 1941. The manufacturing plants of White Motor, Autocar, and Diamond T were collectively churning out an impressive 500 half-tracks per month by mid-1942, a figure that surged to a staggering 1,500 per month by 1943. Total production across all variants ultimately surpassed 41,000 units by 1945. This remarkable output underscores the ingenuity of the American approach. While these may not have been the most exquisitely engineered half-tracks ever conceived, they were undeniably effective, and, crucially, tens of thousands of them were rolling off assembly lines precisely when Allied armies needed them most. In stark contrast to the American engineers' focus on mass production, German designers were consumed by an entirely different pursuit, achieving technical perfection, irrespective of the associated costs. The Sonderkraftfahrzeug 251 (ST), KFZ 251, more commonly referred to simply as the ST, KFZ 251 or, colloquially, the Hanomag after its primary manufacturer, embodied a fundamentally opposing philosophical stance. Where the Americans embraced the principle of good enough is good enough, the Germans insisted that every mechanical component should be engineered to its absolute theoretical limit. This unwavering commitment to excellence rendered their half-tracks extraordinarily capable, yet simultaneously made them absurdly complex and challenging to construct. The very heart of the ST, KFZ 251 was a Maybach HL42 6-cylinder gasoline engine, which produced 100 horsepower, a figure notably less than its American Hercules counterpart. However, a crucial distinction emerges here. Maybach was the same esteemed company responsible for manufacturing the engines powering the formidable Tiger and Panther tanks. Consequently, this was not merely a truck engine repurposed for military service. The HL-42 was specifically conceived and engineered for tracked vehicles, with meticulous attention paid to optimizing torque delivery at lower RPMs. This powerful yet refined engine propelled the 8.5-ton vehicle to a commendable speed of 53 km per hour on paved roads, remarkably, even faster than the American M3, although their cross-country performance remained nearly identical, hovering around 20 to 25 km per hour. The German engine operated at cooler temperatures and with greater fuel efficiency than its American equivalent, but it demanded more frequent and specialized maintenance, utilizing precision parts that required significantly longer manufacturing times. German transmission engineering often bordered on what could be described as over-engineering. The SD, KFC 251 featured a sophisticated Maybach Varirex 128H preselector gearbox, boasting an impressive 7 forward speeds and 3 reverse gears. Consider the implications of such complexity. 7 forward gears. The driver would pre-select the desired next gear using a lever, then merely tap the clutch pedal, at which point the transmission would automatically shift using an intricate vacuum system. When operating as intended, this system offered a smoother and faster shifting experience compared to the American manual transmissions. However, when it inevitably malfunctioned, which occurred with greater frequency, it necessitated the intervention of a highly specialized mechanic and replacement parts that could often take weeks to procure. This encapsulates the German half-track narrative in miniature, technically superior in design, yet logistically nightmarish in practice. The initial operational challenges associated with these vehicles proved to be incredibly complex and, at times, truly nightmarish from a logistical standpoint. The fundamental engineering philosophy of German designers was further elucidated by the sophisticated track system employed on the SD, KFC 251. Diverging significantly from the more common rubber block and cable configurations found in many Allied designs, this German half-track utilized robust metal track links, meticulously interconnected by durable pins, mirroring the construction of traditional tank tracks, albeit with a reduced width. Each side of the vehicle was equipped with 70 individual track links, fabricated from resilient manganese steel and intricately shaped with pronounced grooves to optimize traction. While these formidable tracks demonstrated extraordinary longevity on firm terrains and possessed an unparalleled capacity to withstand severe operational abuse, their inherent metallic composition resulted in considerable noise generation. Furthermore, they were prone to causing significant wear and tear on paved surfaces and necessitated diligent, continuous tensioning and routine maintenance. Nevertheless, German engineers deliberately embraced these compromises, recognizing that the superior performance of metal tracks in the most unforgiving environments, such as pervasive deep mud, accumulating heavy snow, and intensely frigid conditions where rubber alternatives were susceptible to cracking and catastrophic failure, outweighed their operational drawbacks. However, the most profound departure in German engineering ingenuity manifested itself in the distinctive interleaved road wheel system. In stark contrast to the majority of half-tracks, including those developed by American manufacturers, which typically incorporated 4 or 5 road wheels per side affixed to straightforward suspension arms, the SD, KFC 251 boasted a remarkable 7 overlapping road wheels on each flank. These wheels were ingeniously arranged to interlace with one another when viewed from opposite sides, creating a visually striking zigzag pattern across the entire width of the track system, as if one were observing the vehicle from the rear. This innovative interleaved configuration offered a multitude of advantages. It facilitated a more uniform distribution of the vehicle's considerable weight, consequently reducing ground pressure to an even greater extent, and remarkably, provided an exceptionally smooth ride for what was fundamentally a tracked vehicle. Accounts from German soldiers who had experienced the operational characteristics of both captured American halftracks and their indigenous hanemags consistently indicated a universal preference for the German suspension system, underscoring its genuinely superior performance and comfort. Please stay with us and watch the end of the video to uncover all the fascinating details. We would be immensely grateful for your like and subscription. Please also consider leaving a comment below, sharing where you are from and your thoughts on this intriguing video topic. Yet, this seemingly advanced design came with a significant drawback. These complex interleaved wheels were, in practice, a veritable maintenance catastrophe. Should an innermost wheel suffer damage or require replacement, an arduous procedure necessitated the prior removal of several external wheels, transforming a simple repair into a protracted ordeal. Furthermore, operational conditions frequently led to mud, snow, and ice becoming densely packed within the intricate spaces between the wheels, often freezing solid overnight. This particular problem was exacerbated on the brutal Eastern Front, where ambient temperatures plummeted to an unforgiving -40 degrees. Consequently, German crews were compelled to dedicate many hours each morning, armed with hammers and blowtorches, simply to dislodge and free the frozen wheels. A maintenance task that could be accomplished in a mere 15 minutes on a comparatively simpler American half-track frequently consumed up to half a day of precious operational time when performed on a hanemag. The inherent mechanical complexity of the SD KFC 251 was paralleled by its demanding manufacturing process. In 1940, the construction of a single SD KFC 251 necessitated approximately 3,000 hours of highly skilled labor, a stark contrast to the mere 800 hours required for the assembly of an M3 half-track. Throughout the entirety of the conflict, Germany managed to produce approximately 15,500 units of the SD KFC 251, a commendable achievement given their challenging industrial circumstances. Yet this figure represented barely one-third of the total American half-track output. This disparity vividly illustrated a fundamental strategic choice: Germany's emphasis on intricate quality over sheer quantity, a philosophy concretely manifested in the very steel and rubber of their respective military vehicles. The trajectory of military vehicle development took a truly radical turn at this juncture. An innovator, observing these essentially enhanced utility vehicles, posed a revolutionary question. What if we were to mount artillery pieces directly onto them? This proposition, initially appearing audacious, gains profound logical grounding when one considers the inherent limitations of conventional artillery. Historically, traditional field guns were laboriously towed by either trucks or horses, a method that invariably entailed protracted setup times prior to engagement. Furthermore, the imperative to rapidly displace to evade devastating counter-battery fire was rendered virtually impossible under such arrangements. However, by directly integrating the same powerful gun onto a half-track chassis, a new paradigm of mobile firepower emerged, capable of delivering ordnance, swiftly relocating, and consequently enhancing its survivability on the battlefield. Yet, the formidable engineering hurdles inherent in this transformation were unequivocally brutal. The primary and most immediate challenge centered on mitigating the destructive forces of recoil. When a 75 mm gun discharges its projectile, it unleashes approximately 15 tons of immense rearward force within a mere fraction of a second. This colossal kinetic energy absolutely demands effective dissipation. Merely affixing a cannon directly to a half-track's cargo bed would inevitably result in the vehicle being literally torn asunder or violently flipped backward by the sheer force. American engineers, confronted with this profound dilemma while developing the M3 gun motor carriage in early 1941, devised an ingenious multifaceted solution. They securely mounted a French 75mm gun upon a substantially reinforced pedestal, which was then meticulously welded directly to the vehicle's robust frame, rather than its less structural body. Complementing this, they incorporated massive recoil cylinders, essentially sophisticated hydraulic shock absorbers, designed to permit the gun barrel to slide backward by approximately 2 feet upon firing. This mechanism effectively transformed the instantaneous, violent 15-ton impact into a far more manageable, prolonged push distributed smoothly over an entire second. However, the complexities of physics presented further formidable obstacles to overcome. Adhering to the principle that every action elicits an equal and opposite reaction, even with sophisticated recoil management systems in place, the act of firing still imparted a significant jolt to the entire vehicle structure. The ingenious solution to this issue involved the integration of outriggers and spades, robust metal legs designed to articulate downwards from the sides and rear of the vehicle, terminating in broad flat plates engineered to firmly embed themselves into the terrain. Prior to engaging targets, the crew would meticulously deploy these stabilizing appendages, effectively anchoring the half-track immovably in its firing position. A prime example of this necessity was the M12 gun motor carriage, a formidable machine that mounted a powerful 155mm howitzer onto a modified M3 chassis. This vehicle featured an enormous spade at its rear, which absolutely had to be driven securely into the ground before the commencement of each firing mission. Without this critical anchoring device, the sheer force of the howitzer's discharge would literally propel the 26-ton vehicle backward by several feet with every single shot. In contrast, German engineers adopted a distinct strategy with their ST KFZ 251/9 variant. This iteration featured a short-barreled 75mm gun housed within a mount that permitted only limited traverse. Rather than endeavoring to develop a comprehensive mobile artillery piece designed for indirect fire, their objective was essentially to create an assault gun, a vehicle capable of advancing in concert with infantry, delivering devastating close-range fire against fortified bunkers or structures, and subsequently maintaining its momentum. The restricted traverse mechanism inherently reduced structural stress on the vehicle, as the gun was prevented from pivoting to an extent that could compromise the half-track stability. With a maximum elevation of merely 20 degrees, this weapon system was clearly not intended for high-trajectory engagements, such as lobbing shells over intervening hills. Instead, its design optimized it for direct-fire missions against visible targets, typically engaged within an effective range of 800 meters. The challenge of ammunition storage emerged as yet another formidable and complex problem. While a conventional towed artillery piece might have its shells conveniently stacked in a nearby, pre-established protected position, a half-track mounted gun entailed a fundamentally different operational reality. Every single round had to be transported directly aboard the vehicle. This necessity elevated the importance of robust armor protection for the onboard ordnance to a critical level. For instance, the M12 GMC, due to the sheer size and weight of its projectiles, could accommodate only 10 rounds of 155mm ammunition internally. Each shell, weighing a substantial 95 pounds, occupied considerable space. Consequently, These formidable self-propelled guns typically operated in conjunction with an accompanying M30 cargo carrier half-track, which followed closely behind, laden with an additional 40 rounds to sustain combat operations. German armored vehicles encountered analogous limitations regarding onboard ammunition capacity. Specifically, the SD, KFZ 251-9 was designed to carry a comparatively modest total of 52 rounds of 75mm ammunition, which were meticulously stowed in specialized bins strategically located along the vehicle's hull sides, precisely where the protective armor plating was at its most substantial. The development of anti-aircraft variants propelled engineering ingenuity to even greater extremes. The M16 multiple gun motor carriage, for example, incorporated an impressive array of 4.50 caliber machine guns housed within an electrically powered turret, thereby creating a highly effective mobile flak platform. The entirety of this complex turret system, including its dedicated generator, imposed a considerable weight of over a ton and was positioned relatively high, significantly impacting the vehicle's center of gravity. Consequently, engineers were compelled to integrate additional counterweights and slightly augment the width of the track stance to counteract the inherent risk of the vehicle tipping over during aggressive maneuvers or sharp turns. The combined rate of fire for this quartet of machine guns was an astounding 2,400 rounds per minute, a figure that, while initially sounding immensely powerful, gains sobering perspective when one considers it translates to an expenditure of 200 pounds of ammunition every minute. The M16 was designed to carry a total of 5,000 rounds, which effectively provided approximately 2.5 minutes of continuous firing capability before the ammunition supply was exhausted. This operational reality meant that the vast majority of the vehicle's internal volume was dedicated almost exclusively to the storage of numerous boxes filled with linked ammunition. Perhaps the zenith of this conceptual development was the SD, KFZ 251/22, a formidable variant introduced by the Germans in 1944. This particular model featured the potent 75mm PaK-40 anti-tank gun, a weapon capable of penetrating 100mm of armor at a range of 1,000 meters, thereby posing a significant threat even to the robust Soviet T-34 tanks. However, the integration of such a high-caliber, powerful weapon onto a relatively light half-track chassis necessitated extensive compromises across various design aspects. The vehicle's ammunition capacity, for instance, was severely curtailed, limited to a mere 19 rounds. Furthermore, the gun shield provided only minimal protection, as any substantial increase in armor would have critically overloaded the chassis. Critically, firing the weapon from anything other than perfectly level ground presented a significant risk of destabilizing and potentially tipping the entire vehicle. Consequently, crews operating these machines rapidly developed a meticulous approach to positioning, acutely aware that their initial shot might very well be their sole opportunity before they were compelled to rapidly relocate or face potential obliteration from enemy return fire. The emergence of tank destroyers embodies the very essence of desperate, yet brilliant, wartime engineering. By 1942, both the Allied and Axis powers found themselves confronting armored threats for which their existing arsenals were largely unprepared. Formidable German Tiger tanks that effortlessly repelled the projectiles of most Allied guns, resilient Soviet T-34s that routinely overwhelmed German defensive strongpoints, and Japanese armor in the Pacific theater demanding a level of offensive punch far exceeding what standard infantry rifles could deliver. The core dilemma was straightforward. The construction of entirely new, purpose-built tanks was a prohibitively time-consuming and resource-intensive undertaking, a luxury neither side truly possessed in the midst of global conflict. In contrast, the innovative solution of mounting powerful anti-tank guns onto readily available half-track chassis offered a far more expeditious path, one that could be realized within months rather than years. The American M3 gun motor carriage fundamentally represented the very first, hastily conceived attempt at this concept, rapidly assembled in 1941, even prior to the devastating attack on Pearl Harbor. At the renowned Aberdeen Proving Ground, resourceful engineers took standard M3 half-tracks, systematically stripped out the bench seats from the rear compartment, and then ingeniously mounted a 75mm M1897 gun, a design that, remarkably, dated back to World War I, upon a robust pedestal within the vehicle's cargo area. This initial iteration lacked a sophisticated turret or any truly substantial protective features, relying instead on a mere gun shield and, implicitly, a considerable measure of good fortune. Consequently, the five-person crew operated in a highly vulnerable state, completely exposed from the waist upwards. Crucially, despite its rudimentary design, the M3 GMC possessed a vital capability. It could effectively neutralize German Panzer IIIs and early Panzer IVs at a range of 1,000 yards. Between 1941 and 1943, an impressive total of 2,200 units of these vehicles were manufactured. These self-propelled guns first saw active combat service in North Africa, commencing in November 1942, where American forces engaged at Kasserine Pass were subjected to harsh, brutal lessons regarding the undeniable superiority of German armor. The operational performance of the M3 GMCs in Tunisia starkly illuminated the inherent, fundamental flaw of the half-track tank destroyer concept. While it possessed the capacity to inflict considerable damage, it was profoundly incapable of withstanding enemy fire in return. Its side armor, a mere 6.35 mm thick, offered barely sufficient protection against standard rifle rounds, and proved utterly ineffective against anything more substantial. German artillerymen and tank crews swiftly recognized the M3 GMCs as high-priority targets. Their tactical doctrine dictated that eliminating one early in an engagement would effectively neutralize a significant and immediate threat. Detailed American after-action reports compiled from the intense battles surrounding Sidi Bouzid in February 1943 unequivocally demonstrated that M3 GMCs were compelled to engage targets from carefully concealed positions, maintaining a standoff distance of at least 1,200 yards. Furthermore, their operational survival depended on their ability to exploit their inherent mobility to constantly reposition and, critically, to never, under any circumstances, allow themselves to be caught exposed in open terrain. These vehicles, by their very nature and design, function most effectively as ambush predators, rather than engaging in direct, sustained brawling confrontations. Ambush predators, rather than direct combatants, characterized the specialized role of these military vehicles. The German forces, facing an acute operational imperative on the Eastern Front, were compelled by sheer necessity to devise their own half-track tank destroyers. By the close of 1943, the sheer volume of Soviet tank production was overwhelming German defensive formations. Initially, the SD, KFZ 251 and 10 was deployed, equipped with a 37mm Pak 36, an armament already deemed obsolete and capable of scarcely denting the frontal armor of AT-34. Driven by a desperate need for a more formidable solution, German engineers conceived the SD, KFZ 251/22, which mounted the potent 75mm Pak 40, the identical cannon found in their dedicated tank destroyers. Production commenced in 1944, with approximately 175 units manufactured before the conflict's conclusion. This particular vehicle represented a pivotal advancement, genuinely capable of posing a decisive threat to Soviet armored units, boasting penetration values that could reach an impressive 133 mm at 500 meters, using standard ammunition, sufficient to punch through the hull or turret of a T-34 across the majority of typical combat engagements. However, integrating such a formidable piece of ordnance onto a half-track chassis inherently created significant engineering compromises and operational drawbacks. The Pak-40 itself weighed a substantial 1,425 kilograms, exceeding 3,100 pounds. When factoring in the mounting hardware, protective shield, and a full complement of ammunition, the total combat load pushed close to 2 tons, straining a vehicle originally designed solely for infantry transport. Consequently, the SD, KFZ 251/22 became notably nose-heavy, exhibited unwieldy handling characteristics, and its suspension system was under constant, severe stress. Its maximum operational speed plummeted to 40 km per hour, and its cross-country performance suffered a marked and noticeable degradation. German crews frequently reported that operating a fully loaded SD, KFZ 251/22 felt akin to wrestling a stubborn horse, with the steering demanding immense physical exertion, particularly when navigating through challenging terrain like deep mud or heavy snow. The tactical employment of these vehicles was refined through the crucible of combat experience. By 1944, both American and German military doctrines had converged upon strikingly similar principles for these provisional tank destroyers. Half-track tank destroyers proved most effective when deployed from prepared defensive positions, where they could skillfully utilize the natural terrain for concealment and protection, engage enemy armor at their maximum effective range, and execute a rapid, decisive retreat immediately after firing. A prime example occurred during the major Soviet offensive operation in June 1944, where German SD, KFZ 251/22s were strategically employed in small groups, typically comprising 3 to 5 vehicles, positioned discreetly within tree lines or behind earthen embankments. Their modus operandi involved patiently awaiting Soviet armor columns to approach within an 800-meter engagement window, unleashing a concentrated volley of fire, and then promptly displacing to predesignated alternate positions. Survival in such encounters was absolutely dependent on their mobility and the element of surprise, as remaining stationary to engage in a prolonged firefight invariably led to their destruction. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The American experience in France following D-Day revealed remarkably similar patterns in the effective utilization of these vehicles. M3 gun motor carriages, GMCs, provided crucial support to advancing infantry units by establishing overwatch positions from ridge lines, poised to engage anticipated German counterattacks. During the intense fighting around St. Lo in July 1944, M3 crews honed their skills in strategic collaboration with M10 tank destroyers. The half-tracks would often act as decoys, maneuvering to bait German armor into revealing their concealed positions, thereby allowing the heavier, more protected M10s to deliver the decisive shots. This was undeniably perilous work, frequently resulting in high casualties, yet it proved instrumental in curtailing German armor from running rampant through vulnerable American infantry positions. Ultimately, the half-track tank destroyer was never conceived as the perfect solution. Rather, it represented the most viable and available option, hastily constructed and widely deployed out of sheer necessity. The alternative was the grim prospect of confronting formidable enemy tanks armed with little more than bazookas and raw courage. By late 1944, both Allied and Axis forces were systematically phasing out these expedient designs in favor of purpose-built armored fighting vehicles. Nevertheless, for 2 crucial years, these ingenious, improvised hybrids successfully filled a desperate and critical operational void. Stripping away the specialized armaments and the associated combat glory, one uncovers the fundamental, core mission of the half-track: to safely transport infantry into the heart of the battle, ensuring they arrived alive and prepared for immediate engagement. This objective, deceptively simple in premise, reveals its inherent complexity when one delves into the intricate engineering details. Designing an effective armored personnel carrier necessitates a delicate and often contradictory balance of 3 fundamental elements: protection, carrying capacity, and mobility. Excessive armor invariably renders the vehicle too heavy and sluggish to maneuver effectively. Carrying too many soldiers leaves insufficient space for essential ammunition, equipment, or supplies. Conversely, optimizing solely for speed means sacrificing vital protection, leading to catastrophic losses when even basic machine gun fire commences. The M3 half-tracks armor scheme perfectly exemplifies how these complex design calculations were meticulously played out. Its front plate consisted of 12.7 mm of rolled homogeneous steel, strategically angled at 30 degrees. Through the ingenious application of sloped armor physics, this configuration provided effective protection equivalent to approximately 15 mm of vertical armor. This level of defense was deemed sufficient to stop standard 7.92 mm German rifle rounds at 100 meters, and .30 caliber machine gun fire across most engagement ranges. However, the side armor was significantly attenuated, measuring only 6.35 mm thick, barely adequate to resist pistol rounds and shrapnel, but little else. The rationale for such thin side plating was purely pragmatic. Every additional millimeter of steel across the vehicle's 18-foot length added hundreds of pounds. Engineers prudently calculated that 6.35 mm sides represented the absolute minimum necessary to offer reasonable safety for the crew and passengers from fragmentation and small arms fire, while critically maintaining the vehicle's lightness and agility required for mobility across soft, challenging terrain. The interior layout of the M3 was uncompromisingly functional and brutally practical. The driver and vehicle commander occupied individual seats in the front compartment, protected by armored doors that could swing open for access. Behind them, the main cargo area measured roughly 6.5 feet wide by 10 feet long, equipped with simple bench seats running along each side. 10 infantrymen would sit facing inward, often with their knees almost touching, their rifles held vertically or laid across their laps. This cramped arrangement served as strategic imperative to keep the soldiers positioned below the height of the armored sidewalls. To stand up meant immediate exposure from the chest up, rendering them acutely vulnerable to everything from concentrated rifle fire to artillery shrapnel. Consequently, combat-experienced units quickly learned the discipline of remaining seated until the absolute last second before dismounting for engagement. The open-top design of the half-track remains a perennial point of contention and discussion, both during its service and in historical analysis today. The question of why a protective roof was not added is addressed by a multifaceted rationale encompassing 3 primary considerations: weight, situational awareness, visibility, and emergency egress, escape. A steel roof robust enough to provide meaningful ballistic protection would have added at least 800 pounds to the vehicle's mass, pushing it beyond its design suspension limits and dramatically increasing its ground pressure, thereby impairing mobility. More critically, the infantry squad leader absolutely needed an unobstructed view of the surrounding environment during movement to maintain situational awareness. Fully buttoning up the vehicle would have meant effectively driving blind into potential ambushes. Furthermore, in the catastrophic event of the vehicle striking a mine or sustaining a direct hit, an open top afforded soldiers unfettered egress in a matter of seconds, preventing them from being trapped and incinerated within a burning vehicle, a far more preferable outcome than struggling through narrow, compromised doors. The true transformative contribution, however, lay not merely in the half-tracks engineering, but in its profound impact on mechanized infantry doctrine. This is where the half-track fundamentally reshaped the nature of warfare. Prior to 1940, infantry units either marched laboriously on foot or were transported in unarmored trucks, arriving at battlefields either physically exhausted or dangerously exposed. The half-track introduced a hitherto unprecedented tactical option: infantry that possessed the mobility to keep pace with advancing tank columns and arrive at their objectives fresh, organized, and immediately ready for combat. Illustrative examples of this paradigm shift abound. During the North African campaign at El Alamein in October 1942, British and Commonwealth forces effectively utilized American-supplied M3s to follow and capitalize on their armor breakthroughs, exploiting gaps in enemy lines before German defenders could reposition. The infantry arrived at the front lines fresh, with all their equipment intact, capable of dismounting and immediately securing objectives that tanks, by their nature, could not hold alone. The Normandy landings on June 6, 1944, further proved this concept under the most arduous possible conditions. American armored divisions employed M3 half-tracks to push inland from the beaches, transporting infantry through the challenging bocage country where tanks were particularly vulnerable. The typical tactical drill involved half-tracks advancing in column formation behind Sherman tanks, maintaining a distance of 50 to 100 yards. When enemy fire erupted, the Shermans would return suppressive fire, while infantry rapidly dismounted from the half-tracks, utilizing the vehicle's bulk as immediate cover. This streamlined procedure typically took perhaps 15 seconds from the moment of first contact to infantry being on the ground and actively maneuvering. German after-action reports from Normandy repeatedly noted the marked contrast in how quickly American mechanized units could respond to contact compared to their own truck-mobile infantry, who were often forced to dismount farther back and advance on foot. The quantifiable impact of this integration is clearly reflected in the numbers. A standard American armored infantry battalion in 1944 was structured with 3 rifle companies, each comprising 3 platoons, and each platoon containing 4 squads. This organizational scheme amounted to a total of 36 squads, necessitating 36 half-tracks for personnel transport, plus additional vehicles for command and support roles, roughly 50 half-tracks per battalion. These versatile vehicles were not merely personnel carriers. They functioned as comprehensive mobile platforms, transporting .50 caliber machine guns, mortars, essential ammunition, radios, and vital medical supplies. The half-track fundamentally transformed infantry from traditional foot soldiers into mounted troops, thereby dramatically enhancing the speed and flexibility of mechanized warfare. By 1945, the strategic question was no longer whether to mechanize infantry, but rather how to design and build the next generation of vehicles that could execute this critical mission even more effectively. Taking a machine originally engineered in Cleveland for the temperate battlefields of Europe and deploying it into the brutal Russian winter or the suffocating Pacific jungles inevitably exposed the limitations of every initial engineering assumption. The half-track's true and rigorous proving ground was not the controlled testing facilities in Maryland. It was the unforgiving -40 degrees mornings outside Stalingrad and the oppressive 100% humidity of jungle trails in New Guinea. These extreme and unanticipated operational environments demanded radical field modifications that the original engineers never could have foreseen, resulting in numerous variants that often diverged markedly from the initial vehicle design. The Eastern Front represented the stark confrontation where rubber met reality in the most devastating manner for German halftracks. German SD, KFZ 251s began experiencing debilitating malfunctions and catastrophic failures during the severe winter of 1941 to 1942 as Army Group Center relentlessly pushed its advance toward Moscow. Those aesthetically pleasing interleaved road wheels, which provided such a smooth and stable ride in normal conditions, transformed into treacherous death traps when the pervasive mud froze solid overnight between their intricate spokes. Crews resorted to a desperate array of ingenious, yet often futile, expedients, lighting fires underneath vehicles, pouring precious gasoline between the wheels and igniting it, and even utilizing explosive charges to blast the accumulated ice free. None of these improvised methods worked consistently or reliably. Consequently, German field workshops initiated systematic adjustments, welding steel plates over the gaps between the wheels, a modification that undeniably reduced performance but effectively prevented further ice accumulation. By late 1942, factory production lines incorporated these lessons learned, implementing wider wheel spacing and a simplified suspension design specifically tailored for units operating on the Eastern Front, aiming to ameliorate these critical winter vulnerabilities. American M3 halftracks, supplied to the Soviet Union under the crucial Lend-Lease program, encountered a unique array of operational difficulties upon their arrival. Between 1942 and 1945, Russian forces received approximately 1,100 M2 and M3 variants, and almost immediately, ingenious Soviet mechanics began implementing a series of essential modifications. The most pressing concern revolved around their cold start capability. The Hercules engine, a robust power plant in temperate climates, suffered from a critical flaw. Its carburetor would invariably freeze solid in the severe sub-zero temperatures prevalent on the Eastern Front, rendering starting impossible without a protracted and often impractical preheating process. To counteract this, Soviet workshops engineered and installed engine block heaters, meticulously insulated fuel lines, and recalibrated carburetors with different jet sizes, specifically designed to handle the increased viscosity of gasoline in extreme cold. Furthermore, these workshops creatively fashioned wooden enclosures to cover the otherwise open cargo areas, effectively transforming the standard open-top personnel carriers into rudimentary yet highly effective enclosed vehicles that offered vital protection against the biting wind chill during lengthy troop movements across the vast, frozen plains. The challenges extended to the vehicle's track performance, particularly when confronted with deep snow, demanding truly radical engineering solutions. The standard rubber block tracks, while functional in other environments, proved entirely inadequate. They would rapidly accumulate snow, which would then compact and freeze into slick ice, completely obliterating any vestige of traction. Both German and Soviet forces, facing similar environmental adversaries, independently experimented with groussers, robust metal cleats meticulously designed to be bolted onto the existing track blocks. These groussers function much like climbing crampons, digging aggressively into the snow and ice to provide desperately needed grip. The Germans, in particular, developed their Winterketten, winter kit, a sophisticated system of special track extensions that dramatically increased the track surface area by nearly 40%. This significant augmentation effectively lowered the ground pressure to such an extent that these modified half-tracks could traverse snowdrifts deep enough to completely engulf conventional wheeled vehicles. While the installation of these track extensions was an arduous and time-consuming task, often requiring hours of labor in intensely freezing conditions, military units that neglected this crucial preparation before launching winter offensives frequently found their vehicles immobilized and useless within mere days. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Conversely, the Pacific Theater presented a diametrically opposite yet equally brutal set of environmental challenges. The relentless combination of intense heat and pervasive humidity wrought havoc on the half-track's intricate electrical systems, accelerated the corrosion of metal components, and transformed the vehicle's interiors into oppressive soundness capable of inducing severe heat exhaustion in personnel within minutes. American forces deployed to New Guinea, commencing in 1943, encountered terrain that initially rendered half-tracks seemingly useless. Dense, impenetrable jungle, treacherously narrow trails, expansive swamps, and numerous rivers devoid of bridges. Despite these formidable obstacles, Marine and Army units displayed remarkable ingenuity, discovering innovative and often unconventional applications for these vehicles. Engineers, for instance, undertook radical field modifications on some M3s, entirely removing the front wheels and extending the tracks forward. This ingenious adaptation created fully tracked vehicles with a significantly lower ground pressure, proving indispensable for navigating treacherous swamp crossings. These field-modified monsters, though appearing absurd in their unconventional design, possessed an unparalleled ability to traverse thick, clinging mud that would utterly immobilize all other forms of transport. Japanese forces, during their encounters with American half-tracks throughout the Philippines campaign of 1944 to 1945, were genuinely perplexed by these hybrid vehicles. Japanese military doctrine, at the time, placed a strong emphasis on light tanks and infantry units that relied on truck mobility, viewing half-tracks as unnecessarily complex and excessively maintenance-intensive. In truth, their assessment was not entirely unfounded. In the unforgiving tropical conditions, both the sophisticated American and German half-tracks demanded an almost constant regimen of meticulous maintenance. The ubiquitous humidity relentlessly corroded electrical connections, while the pervasive jungle mud infiltrated every bearing and joint, and organic debris frequently clogged critical cooling systems. Units operating in these challenging environments quickly learned to implement a rigorous twice-daily maintenance schedule, which effectively amounted to a complete rebuilding of critical systems every few weeks, just to keep the vehicles operational. The stories gleaned from captured vehicles offered fascinating insights into the desperate measures of adaptation. Soviet forces, for example, captured hundreds of German SD, KFZ, 251 half-tracks during the major offensives of 1943 to 1944. Despite facing severe shortages of specialized ammunition and spare parts, these vehicles were immediately pressed into service. Soviet crews, with characteristic resourcefulness, often welded on additional armor plates scavenged from destroyed tanks, thereby creating what were colloquially termed Frankenstein vehicles, heavier and slower, certainly, but significantly better protected. Some Soviet-operated Hanemags underwent even more radical transformations, receiving entirely new armament systems, 85mm recoilless rifles, formidable Katyusha rocket rails, and even flamethrowers were integrated onto their chassis. While the original German engineers would undoubtedly have been horrified by such mechanical impurities, Soviet military doctrine consistently prioritized maximum firepower and combat utility over pristine mechanical design. Operations in the vast, arid expanse of the North African desert necessitated yet another distinct set of modifications. The omnipresent fine sand infiltrated virtually every mechanical component, drastically accelerating engine wear and reducing their operational lifespan to a mere fraction of what was considered normal. British forces, utilizing American M3s during the Western Desert Campaign commencing in late 1942, installed massive air filters, some towering nearly 3 feet in height, specifically to safeguard their engines from the destructive ingestion of sand. They also replaced the standard tracks with specialized desert pattern tracks, featuring wider blocks designed to provide superior flotation in the soft, shifting sands. Water, both for the vehicles and their crews, became an absolutely critical consideration. Vehicles operating in the Sahara frequently carried additional radiator coolant, and often towed dedicated trailers laden with nothing but water cans. The fundamental, overarching lesson derived from these diverse adaptations was clear. The half-track was not a singular, monolithic vehicle, but rather dozens of distinct variants, each meticulously evolved and customized to survive the specific, hellish environments that would have rendered the factory standard version utterly inoperable within a matter of weeks. By 1946, as the dust of global conflict settled, thousands of half-tracks lay dormant in motor pools stretching from Fort Knox in the United States to Frankfurt in Germany. Military planners, facing the harsh realities of peacetime, found themselves confronting an increasingly uncomfortable query: what precisely should be done with these machines? The war had concluded, and in the brutally clear light of post-conflict analysis, the half-track's fundamental design compromises became impossible to overlook. It occupied an awkward middle ground, being neither fully a truck nor truly a tank. In the context of the nascent Cold War world, this ambiguous tactical position suddenly appeared to be a strategically untenable dead zone. The Korean War, raging from 1950 to 1953, was initially perceived as the half-track's potential comeback tour. American forces, with expectations rooted in their European experiences, dispatched M3s to the peninsula. However, Korea, with its unique and unforgiving terrain, mercilessly exposed every inherent weakness that the urgency of wartime production and deployment had previously masked. The peninsula's rugged, mountainous landscape proved devastating to transmissions and suspensions that had been engineered for the comparatively smoother roads of Europe. The rubber track blocks, which had performed adequately on French soil, rapidly disintegrated on the abrasive Korean granite, often lasting a mere 400 meters before demanding replacement. The maintenance requirements were nothing short of absurd. A single M3 half-track typically necessitated approximately 40 man-hours of upkeep per week just to remain operational, a stark contrast to the mere 10 hours usually required for a conventional truck. Consequently, commanders increasingly opted to leave these problematic vehicles in their motor pools, instead prioritizing the requisition of more reliable trucks. However, the truly decisive factor in the half-track's decline was a profound tactical mismatch with the evolving nature of combat. Korean warfare was characterized by significantly longer engagement ranges than anticipated, with infantry battles frequently unfolding at distances of 600 to 800 yards, rather than the close quarters, bocage, fighting that had defined Normandy. The half-track's 6.35 mm side armor, which had barely offered protection against rifle rounds in 1944, proved absolutely useless against the more potent Soviet-supplied weaponry utilized by North Korean and Chinese forces by 1951. Even the 7.62 by 25 rounds fired by a PPSH-41 submachine gun could penetrate those thin sides at a range of 200 yards, while heavy machine guns quickly transformed half-tracks into veritable Swiss cheese. Commanders swiftly learned that deploying M3s anywhere near the front lines inevitably led to unacceptable casualties among their soldiers. Concurrently, military engineers were busily designing something entirely new and innovative. The M113 armored personnel carrier, a groundbreaking development, emerged from the Ordnance Tank Automotive Command in 1956. This vehicle represented a complete antithesis to the half-track. It was fully tracked, not a hybrid. It utilized lightweight aluminum armor instead of heavy steel, offering equivalent protection at half the weight, and critically, it possessed inherent amphibious capabilities. Most importantly, the M113 was conceived and designed from the ground up as a dedicated personnel carrier, rather than being an adaptation of an existing truck chassis. The M113 demonstrated a superior ability to traverse rivers, withstand mine blasts more effectively than half-tracks, and its lower profile presented a significantly smaller target to enemy fire. The first production units began rolling out in 1960, and by 1963, the prevailing sentiment was undeniable. This new machine represented the undeniable future of armored troop transport. The underlying engineering philosophy had undergone a complete and irreversible transformation. Half-tracks were emblematic of 1930s thinking, essentially an attempt to combine proven truck technology with tracks, and simply hope the amalgamation would prove effective. The M113, by contrast, embodied the principles of modern systems engineering. It began with a clear definition of mission requirements, then meticulously designed every single component to function synergistically, optimizing the entire system for the actual combat environment it would face. The M113's powerful Detroit Diesel 6V53 engine generated 215 horsepower, nearly 50% more power than the venerable Hercules engine, while simultaneously weighing less and running on more efficient and safer diesel fuel instead of gasoline. Its advanced torsion bar suspension system provided a significantly smoother ride quality and required substantially less maintenance compared to the half-track's older vertical springs. Ultimately, a rigorous cost analysis delivered the final, decisive blow to the half-track's continued viability. By the early 1960s, maintaining the dwindling number of half-tracks still in the U.S. inventory had become more expensive on a per-vehicle-mile basis than acquiring brand-new M113s. Spare parts for the half-tracks were increasingly scarce, given that their production had ceased entirely in 1945. Furthermore, the generation of mechanics who possessed the specialized knowledge to service the old white motor transmissions were steadily retiring. In stark contrast, M113 production was rapidly accelerating, benefiting from modern manufacturing techniques that drove down per-unit costs to below $40,000, a considerable sum in 1960, but an undeniably more cost-effective solution than the continuous struggle to keep 15-year-old, obsolete vehicles operational. The international market mirrored this definitive shift. Israel, for instance, acquired hundreds of surplus American half-tracks in the 1950s and employed them extensively, even through the intense 1967 Six-Day War. Yet, even they had initiated a comprehensive conversion to purpose-built armored personnel carriers by the 1970s. Soviet forces completely abandoned half-track designs after World War II, transitioning directly to fully tracked APCs, such as the BTR-50. The French military retained their half-tracks for the longest duration, operating some into the 1970s in various colonial conflicts, primarily due to economic constraints that prevented a wholesale replacement of their vehicle fleet. The ultimate demise of the half-track was not a consequence of battlefield failure. These machines, in their historical context, performed adequately. Rather, their obsolescence was driven by the relentless march of military evolution. Warfare was rapidly becoming faster, hitting harder, and demanding highly specialized solutions rather than versatile compromises. The M113 and its subsequent descendants offered unparalleled capabilities. They could swim, provided NBC, nuclear, biological, chemical, protection, mounted heavier weaponry, and, most crucially, significantly enhanced the survivability of infantry in an era characterized by ubiquitous automatic weapons and increasingly lethal artillery. By 1970, virtually every modern military establishment had arrived at the same unequivocal conclusion. The choice was now between tracks or wheels, and a definitive selection had to be made. The era of the hybrid vehicle was unequivocally over. The conclusion of a significant chapter in military engineering had arrived. The era characterized by hybrid vehicle designs was undeniably drawing to a close. This period, marked by innovative attempts to fuse disparate propulsion systems, specifically the integration of wheels and tracks, was giving way to new paradigms of military mobility. Engineers, driven by the exigencies of an evolving battlefield, had long experimented with configurations that sought to blend the speed and maneuverability of wheeled vehicles on paved surfaces with the superior off-road traction of track systems. This ambitious, often experimental, phase of development represented a pivotal moment in the quest for the ideal troop transporter and combat support platform, a quest that would ultimately lead to more specialized and purpose-built machinery. The final American half-track vehicles, a staple of mechanized forces for over 2 decades, were officially phased out from active military service around the year 1964, thereby concluding an impressive 23-year operational tenure. This cessation marked a significant inflection point in military logistics and combat strategy, as armed forces globally began to pivot decisively towards more specialized designs tailored for specific battlefield roles. While their primary function as rapid personnel carriers gradually diminished, many of these remarkably robust machines found renewed purpose through extensive repurposing. They embarked on new missions as indispensable engineering vehicles, heavy-duty recovery trucks, or even sophisticated mobile command posts, showcasing the inherent versatility of their chassis. However, the archetypal personnel carrier configuration, once ubiquitous, progressively disappeared from frontline units, reflecting a shift in tactical doctrine. In the contemporary landscape, the dwindling number of operational examples are predominantly preserved within the hallowed halls of military museums or carefully curated private collections, standing as veritable mechanical fossils. These preserved units offer a fascinating glimpse into a bygone epoch when design engineers harbored the ambitious, perhaps even quixotic, aspiration of creating a singular, omnicompetent vehicle capable of fulfilling every conceivable operational requirement. Ultimately, this grand vision proved unattainable, as the increasing complexities and diverse demands of modern warfare necessitated specialized solutions. Nevertheless, for a critical period spanning approximately 1 desperate decade, a time characterized by urgent global conflicts and an immediate, pressing demand for rapidly deployable motorized infantry, the half-track's inherently imperfect yet brilliantly practical compromise offered precisely the adequate solution required, filling a crucial operational void during a tumultuous chapter in military history. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic.